So, okay, thank you everyone for coming to this seminar. Today we are glad to have Dr. Bao here from Idaho National Lab. Dr. Bao is a computational scientist in the Department of Digital Reactor Technology and Development at the Idaho National Lab. And he got his PhD degree from the Department of Nuclear Engineering from North Carolina State University. Since joining Idaho National Lab, Dr. Bao has been working different research projects or programs, such as Light Water Reactor Sustainability Program and the Integrated Energy System Program. Currently, he's leading a digital IC risk assessment project under the Risk-Informed System ANSYS pathway of LWRS program. His research interests including machine learning application in nuclear thermal hydraulics and plant modelization, risk assessment, and PRA application in digital IC design optimization, economic analysis of integrated nuclear system. Now let's welcome Dr. Bao.
Okay, thank you, Jim, for your nice introduction. It's a pity that I cannot come to visit you guys in person because of the travel policy. So today I will introduce one of the projects I'm working on. It's about the safety evaluation and the design optimization of the safety-related digital IC systems in nuclear power plants. And this work is funded by the US DOE Light Water Reactor Sustainability Program Risk-Informed Systems Analysis Pathway. So this project aims to support the transition from analog to digital IC technologies. Compared with the analog IC, the benefits of digital IC systems include the reliable system performance in terms of accuracy and computational capability, the high data handling and storage capabilities to fully measure and display the operating conditions, and some improved capabilities. But there are still some technical barriers for the implementation of digital IC systems in the nuclear power plants, including the unique characteristics of digital IC systems, the potential for software-based Comcast filters, the licensing process for the regulatory review and approval for digital IC system designs and upgrades is difficult, time-consuming, and largely customized for different designs, and also a lack of the consensus on issues underlying the evaluation and adoption of digital IC technology. So addressing Comcast filters is one of the focuses of this project. The goal of this project, as we said before, is to support the transition from analog to digital IC technologies. One of the biggest concerns coming with the plant digitalization is how to address and deal with Comcast filters in these high safety, significant safety-related digital IC systems. A Comcast filter is a malfunction of two or more plant components or functions due to a single filter source. CCFs have the potential to generate unanalyzed events or sequences that may be not bounded by previous plant accident analysis, which may challenge the plant safety. So there are some technical challenges remaining in the CCF analysis, especially for the software CCFs. The first one is how to deal with these Comcast filters. The current strategy is, once identifying the Comcast filters, we need to eliminate them by adding diversity in the software, hardware, or equipment, or the designs. So in this way, the safety margin is surely increased, but also, but so is the cost. So instead of eliminating all of these potential CCFs, which is impossible somehow, another option is to carefully analyze their root causes and coupling factors, quantify their probabilities, and evaluate their impacts to the system and the plant safety, so the decision makers can decide whether that Comcast filter should be a concern or not. The second challenge here is how to fully address Comcast failures in the high safety significant safety-related digital INC systems. In the past decades, various methods have been developed for the hazard analysis, including the FMEA, STPA, HAZCAS, or HAZOP. They have different advantages, but they were not developed for the identifying Comcast failures, especially for the software Comcast failures. The third challenge here is, should software Comcast failures in digital INC systems be addressed qualitatively or quantitatively? Most of these existing approaches focus on the identification of software failures, but neither the identification of software Comcast failures nor the quantification of their probabilities. Instead, the current choice is to perform a conservative bounding assessment to evaluate their impacts to the plant safety, for example, the change of core damage frequency. So the software Comcast failure probabilities are assumed to be 0 or 1 for the risk importance analysis, which may underestimate the safety margins increased in this plant digitalization process. So that is why the quantitatively estimating the risks of potential Comcast failures is very important, because it can provide more risk information to ensure the digital INC designs are cost effective. Therefore, there is a need to develop an integrated risk assessment strategy, including both qualitative hazard analysis and quantitative reliability and consequence analysis to fully address these software Comcast failures in these high safety significant safety-related digital INC systems. The goals of the RESHA efforts on the digital INC risk assessment include providing a best estimate risk-informed capability to estimate the safety margin obtained from the plant digitalization, developing an advanced risk assessment strategy to support the transition from analog to digital technologies, assuring the long-term safety and reliability of vital safety-related digital INC systems, and reducing uncertainty in costs and supporting integration of digital INC systems in the plant. So the strategy or the technology we developed in this project is called Integrated Risk Assessment for Digital INC Systems, IRADIC. The IRADIC includes two phases or two parts, risk analysis and risk evaluation. Risk analysis aims to identify the potential failures of digital-based systems, estimate their failure probabilities, and analyze relevant consequences. So the results from the risk analysis will be compared with some specific risk acceptance criteria in the risk evaluation stage. This figure displays the schematic of the IRADIC, and the task of IRADIC is to evaluate whether the risk from digital failures can be acceptable at the component level, system level, and plant level. Then provide some suggestions to reduce these potential risks in both design stage and operation and maintenance stage. For example, whether we need to eliminate the root causes of some Comcast failures to increase the availability of the system, whether we need to increase the reliability of some important components because they are very important for the success of that. They're very important for the availability and reliability of the entire digital INC systems. So this information can be provided based on the analysis from IRADIC. IRADIC also aims to provide a modularized platform for INC designers, software developers, plant engineers, and risk analysts to efficiently predict and prevent risk by identifying the crucial failure modes, quantify the reliability of the digital INC systems, and evaluating their impacts. In IRADIC, a redundancy-guided system theoretic hazard analysis method was developed to address both hardware filters and the software filters, individual filters and the Comcast filters. It's called RESHA. RESHA can also qualitatively analyze the effects of these filters on system availability. More details about RESHA will be provided in the following slides. So the second part of IRADIC is a multi-skill reliability analysis with tasks of quantifying the probability of filters identified from the hazard analysis and also the filter of the entire digital I&C systems. In IRADIC, two methods have been developed for the software reliability analysis in different state conditions. One of them is called Bahamas, the Bayesian and HRA-aided method for reliability analysis of software. It was developed for the data limited condition, especially for the very early design stage of the software. Another method is called OCRS, orthogonal defect classification for assessing software reliability. This method was developed for the data-rich condition when the software design is mature and the testing or the operational data of the software is available. So that's the second part of the reliability analysis of IRADIC. The third part and also the final part is the consequence analysis. Consequence analysis is applied to evaluate the impact of the consequences from the digital filters to the plant responses or to the plant safety. So all of these risk analysis processes will provide different information, including the filter modes of the system filter probabilities, the estimation of the filter consequences, and based on this information, some suggestions can be provided to optimize the designs of the software or the digital I&C system and also their upgrades by quantitatively reducing the risks and costs. Okay, so we also expect IRADIC to become an integrated risk-informed tool to support vendors and utilities to meet the regulatory requirements and optimize their diversity and the defense in-depth applications in the digital I&C designs and upgrades. The estimated safety margins predicted by IRADIC should be higher and more accurate than using conservative bonding assessment approaches. The safety improvements introduced by these new digital designs are expected to be more significant and can be presented more clearly. So, for example, currently it's thought that all of these common cause filters need to be fixed by adding diversity, which also costs a lot. But in fact, some of these common cause filters do not have significant impacts on the change of core damage frequency or large early release frequency. So the IRADIC can evaluate the impacts of the single software common cause filters to the digital I&C systems and even the plant safety, based on which suggestion can be provided to optimize their designs. For example, which level of redundancy is needed. The figure here shows a 4-division digital reactor trip system, division A, division B, C, and D. These 4 divisions perform the same function to trip the reactor. So the results from IRADIC can help us to determine which level of redundancy is needed. 4 divisions or only 2 divisions is good enough, is safe enough, and how much safety margin can be increased from a 2-division design to a 4-division design, and does it worth to increase the redundancy because each division, the design and the installation of each division costs a lot. Another thing we can help for the design is to determine the level of diversity. For example, does the system needs the design diversity? Does the system needs an analog system with a digital system? Does the system need the software designs to be diverse in the design requirements or programming languages, or does this system needs a diversity in the equipment, meaning different manufacturers, different designs or architectures? So by comparing the risk and cost of different redundant and diverse designs, cost can be saved if some common cost filters are proved to be insignificant to the plant or to the system safety. Okay, so IRADIC is also expected to provide technical basis and risk-informed insights to assist NRC and industry in formalizing licensing processes relevant to addressing common cost filter issues in the different safety-related digital INC systems. This figure illustrates how the IRADIC can support to formalize the licensing process of the digital INC designs and upgrades. The NRC BTP 719 clarifies the requirements for acceptable methods for addressing common cost filters, including identifying common cost filters, reducing common cost filter likelihood, and evaluating common cost filter impacts in design-based events. So the capability of IRADIC in hazard, reliability, and consequence analysis match well with these requirements. So next, I will briefly introduce these three parts of IRADIC: hazard analysis, reliability analysis, and consequence analysis. Okay, so the first part is hazard analysis. For IRADIC, we developed an approach which is called redundancy-guided system theoretic hazard analysis, the RESHA. RESHA incorporates the concepts of combining FTA and STPA from HAZCADs. FTA means fault tree analysis, which is a traditional PRA method. STPA means systems theoretic process analysis. This method was developed by MIT, which is also a hazard analysis method. It has been widely applied for identifying the software filters or the filters in the interactions between different components in a system. HAZCADs is another hazard analysis developed that is developed by APRI and Sandia National Laboratory. So in RESHA, we incorporate these methods. Specifically, we use the FTA to identify the hardware filters, STPA to identify the software filters, and HAZCAD is applied to integrate these two filter modes together. So, in RESHA, the STPA is reframed in a redundancy-guided way to address the common cost filter concerns in the highly redundant digital INC systems, because STPA was not developed for identifying the common cost filters. RESHA also identifies the filters in the type 2 interactions, which means the interactions between different digital components of the digital INC system. So here is a workflow of the RESHA in IRADIC. So after these 7 steps, the results will be compared with the risk evaluation acceptance criteria number 1. Does the individual digital-based filter leads to the loss of the function of the digital INC system? If the answer is no, it means there is no single point of filters in this system. So it should be okay for the application. But if the answer is no, it means there are some filters that can directly lead to the loss of the function of this digital INC system. So that filter needs to be fixed. Okay, so in the following slides, I will provide more information about the method and also the case study. Step 1 is to create a detailed representation of the system of interest. So, the case study shown here is a 4-division digital reactor trip system. The 4 divisions perform redundant reactor trip functions. So in this step, So step one will specify the boundary and the scope of the system, and this analysis details the hardware and software applied in this system, and also map out the system. For example, the first part of the reactor trip system is called reactor protection system. And after that, there is also the manual control from the main control room and reverse shutdown room, which is coming from the operator. A diverse protection system, which is called DPS, is also introduced here. So this reactor trip system includes the manual control and automated control by RPS, meaning the reactor protection system, and also the control from the diverse protection system. It's a very redundant and diverse system. Okay, step two. So step two is applied to build up a flow tree which only includes the hardware feeders. So first of all, the top event of the interest should be defined in different accident scenarios. For example, the feeder of reactor trip system, or the reactor trip system sends spurious trip signals to the breakers, to reactor trip breakers. In this case, we just use the feeder of reactor trip system as an example. So software, which is an INL developed PRA2, is applied to build up this flow tree, and here is a flow tree which only includes the hardware feeders. And step three is to determine the unsafe counteractions by applying the STPA. This is a key step of RESHA. For example, here is a 4-division RTS. It has different levels of redundancy. The multiple reactor trip breakers, which control the control rods, and LCL, different LCL processors in the LCL cabinet, and also different bistable processors, BP1, BP2, in different divisions. So we can see that this system has different levels of redundancy. Let's take the LCL processors as an example. First of all, there are 4 divisions. Each division has two racks in the LCL cabinet, and each rack has 2 LCL processors inside. So it means there are 3 levels of redundancy: the division level, the unit level, it means 2 racks per division, and also the module level, it means 2 processors per rack. So that's why we need to build up a multi-layer control structure that can help us to capture the unsafe counteractions in different levels of redundancy. And in this case, for the LCL processor feeder, we have 3 levels of Comcast feeders. For example, the Comcast feeders of the 2 LCL processors in this rack, or the Comcast feeders of 4 LCL processors in division D, or the Comcast feeders of 16 LCL processors in all divisions. Okay, so step 4 and 5 is to construct an integrated flow tree by adding the applicable unsafe counteractions as basic events into the flow tree, which only has hardware feeders. This table shows some examples of unsafe counteractions. There are different types of unsafe counteractions for one counteraction. For example, type A is defined as the counteraction is needed but not given. For example, during the station blackout, the trip signal is needed but not given by the reactor trip system. Type 2 is the counteraction is given but it's not needed. For example, the reactor trip system just sent a spurious signal to trip the reactor, but actually it's not needed. Type C is the contraction is given too early, too late, or in wrong order. And type D is the contraction is applied too long or stopped too soon. So here we use this contraction 25 as an example. This contraction is division A, selective processor 1 demands the reactor trip breaker A1 to trip the breaker. So the type A of the use A is this processor does not provide trip command to the breaker when it's needed. And type 2 or type B is this processor provides trip command, but it's not needed. Type C is this processor provides trip signal when, but after it's needed for a while. And type D is not applicable because sending that trip signal, we don't need, I mean, sending that trip signal does not need to last for a long time. It's just push that button, or it just need a very short time to perform that action. So, so in this case, only type A and type C is applicable for the top event of the failure of reactor trip system. So next step is to add these two types of unsafe contractions into the fault trees, including their individual failures and also the common cause failures identified in step 3. Okay, step 6 is to determine the K common cause failures that may lead to the single points of failures in the design. In the previous steps, both hardware failures and the software failures and also their common cause failures can be identified. And here we only list 13 common cause failures that may lead to the failure of the reactor protection system. These common cause failures are in the system level, which are suggested to be fixed in the design stage because they are considered as a potential single point of failures. They can just lead to the failure of the reactor protection system. Of course, there are some other common cause failures which are not single points of failure. So that's why we need the quantitative reliability analysis to determine their impacts to the safety or to the system or the plant safety. This table shows the different cut sets for different systems. For example, if we take the full reactor trip system model into consideration, there is no first order cut set. If we only consider, if we do not consider the manual control from the operator or the main control room, there is still no first order cut set, but there are 52 second order cut sets. If we only consider the reactor protection system, there are 13 first order cut sets. So that's how we get the table 5. Okay, so the next step is to identify the cause factors of the critical failures in the design. Okay, the mechanism of the hardware common cause failures has been studied for decades. So the challenge here is to identify the cause factors of these software common cause failures. There are two categories of these of the unsafe contractions of a digital controller or the software failures. Category 1 is the inner software failure, including the software design defect and software implementation failures. Category 2 is the incorrect feedback or inputs to the digital controller. It means the unsafe information flows from the dependent intermediate modules. So according to the difference in the functionality, there are normally two types of digital modules in the DI&C systems. For example, the digital controllers or the intermediate digital module. The physical element of the digital controller include a central processing unit along with its associated microcode, memory, and the INC program. A digital controller may be connected to other controllers or just the intermediate modules. For example, the sensors, the actuators, or even input and output modules. And unsafe information flow is regarded as any received signal external to the controller that is erroneous or falsified or incorrect. So here, a causality relationship diagram between the unsafe information flow, unsafe counteraction, and defined hazards and losses to the stakeholders is shown to illustrate how the unsafe information flow is connected with the unsafe counteractions and other hazards and losses. So, for example, if we can just treat the core damage as a loss, as one of the losses, and then the failure of the reactor trip system can be considered as one of the hazards that may lead to the core damage. Then these unsafe contractions can be considered as the cause factors of these defined hazards or losses. Unsafe contractions are the software feeders from the digital controllers, and the unsafe information flow can be considered as cause factors of these unsafe contractions. So that's the relationship between these different concepts in the RESHA. Okay, so this slide shows the information flow of RESHA. The key outputs of RESHA include an integrated fault tree, which is unquantified because we don't know the probability of the basic events of this fault tree, and also the single point of feeders and their cause factors. These single point of feeders may need to be fixed before this system is applied for different reactor, for different nuclear power plants. And another output of RESHA is a hazard defense plans. Okay, so based on this, according to this information flow, the RESHA, from step 1 of RESHA, a system sketch can be obtained, and then step 2 will build up a hardware fault tree. Step 3 will identify the different contractions and build up a multi-layer contraction. Then step 4 will integrate the hardware feeders and unsafe contractions and build up an integrated fault tree. Step 5 will identify the different comcast feeders based on the levels of redundancy and levels of diversity. Then step 6 will identify the different single points of feeders and calculate the minimal cut sets. And step 7 will identify the different causes of the comcast feeders. So finally, the integrated fault tree and the causes of different feeders will be applied in the following IRADIC reliability analysis, and the single point of feeders will be provided to the system designer or to the risk analysts for further analysis to see whether the system need to be improved or modified. Okay, so as a summary, RADIC-RESHA informs engineers of system vulnerabilities, allowing them to make defensive strategies and incorporate safety measures to ensure a system is successful. Okay, so that's the hazard analysis of RADIC, and next step is the multi-skill quantitative reliability analysis of RADIC. It's called multi-skill because it includes both small-scale software reliability analysis and large-scale DI&C system reliability analysis. The goal is to estimate the DI&C system reliability by calculating the integrated fault tree of the DI&C systems obtained in the previous hazard analysis, and then provide inputs for the following consequence analysis. So this slide just illustrates the framework of IRADIC multi-skill reliability analysis. The first step is the adequate collection and evaluation of design and requirements documentation. The software design information should be collected, which includes the software implementation and testing information, the software design document with the detailed design information, the software requirement formulation with the high-level design information. So all of this design information will be collected and evaluated to see whether this data or information is sufficient enough for a detailed software reliability analysis. And at the same time, the RESHA results will be provided for different purposes. Okay, so if the answer is no, it means the available data is very limited. So for this condition, we developed a method which is called Bahamas in IRADIC. Bahamas applies the Bayesian belief network and HRA method to quantify the failure probability of the software. Normally, Bahamas can be applied in the early stage of in the early design stage of their software or digital INC system, or when the data is very limited, because Bahamas just assume that the software failures, the root causes of software failures are the human errors during the software development lifecycle. So in that way, we do not need much data for the quantification work. We can just apply HRA to quantify the human faults or human errors during the specific software development lifecycle, and they use that information to quantify the software failure probabilities. Okay, so that's for the data limited condition. But if the data is sufficient, then we are developing another method which is called AUKUS to provide a more accurate estimation of the software reliability or software failure probabilities. And AUKUS applied different testing methods, orthogonal defective classification to connect the software defect and the unsafe counteractions identified from the hazard analysis, and then use software reliability growth modeling to quantify their failure probabilities. So after quantify the failure probabilities, the cost failure modeling and estimation will be performed to quantify the probability of cost failures and the probability of individual failures, because the software failure probability calculated by the Bahamas and AUKUS is just the total failure probability of the software, which can be considered as a summation of individual failures, individual failure probabilities, and also the CCF probabilities. And in this step, a modified bit factor model is applied. So after quantifying the cost failure probabilities and individual failure probabilities, we have the probabilities for the basic events of that integrated fault tree. So the next step is to quantify that fault tree and estimate the failure probability of the entire digital INC systems. So after that, we can get the failure probability of the digital INC system, and then we can compare it with the risk evaluation acceptance criterion to see how reliable is a digital system with the identified digital failures, whether it's acceptable or not. Some importance analysis can be applied for different components to see which component has a higher weight to the safety, to the system safety, and accordingly, some improvement or modification of the system can be made. For example, increasing the reliability of some specific components which are very important to the system safety. Okay, so at the same time, the quantified fault tree will be used as an input for the following IRADIC consequence analysis to evaluate the impact of the software feeders to the plant safety. Okay, so here is a this slide just compares Bahamas and AUKUS, which are two methods we developed in IRADIC for the quantitative software reliability analysis. Bahamas is called Bayesian and HRA-aided method for the reliability analysis of software. It was developed for the conditions with very limited data or operational data, conditions with very limited testing or operational data, or for the reliability estimation of the software in very early design stage, which means the data is not sufficient for an accurate estimation of the software failure probability. So Bahamas can just provide a very rough estimation of the failure probability to support the redesign of the software and the target DI&C systems. It's very useful when the data is not sufficient or is very limited, especially when the design is not mature and there's no testing data. Okay, the second method, AUKUS, is called orthogonal defect classification for assessing software reliability. It's still under development, and it's developed for the conditions with sufficient testing and operational data. The goal of AUKUS is to provide a relatively accurate estimation of the software failure probabilities, compared with Bahamas. So in this way, So in this way, we are trying to make IRADIC practical and feasible for different data conditions. The goal is to reach a data method consistency. It means IRADIC can be used and useful for different conditions, for any condition. This table compares the features of Bahamas and AUKUS. They have their own applicable conditions, their own assumptions, their own ways to identify root causes and quantify the failure rates of these root causes. So due to the time limit, I will not provide more information about these two methods. And when we performed this case study, the public data about the software is very limited. So we just use Bahamas to quantify the software reliability or software failure probabilities. Okay, so the next step is to perform the CCF modeling and estimation. And this slide just provides some background about CCF modeling and estimation. So a CCF, or a Comcast failure, is a result of the existence of two main factors: failure cause and a coupling factor that just creates a condition for a failure cause to affect the malfunction of multiple components. The identification of coupling factors and the failure cause is an essential part of the Comcast failure analysis. There are different common coupling factors. For example, the design, the hardware, the software, the function, installation, maintenance, procedures, interfaces, locations, and environment. So a common cause component group should be defined for the Comcast failure modeling and estimation. A Comcast component group is defined as a group of components which share similarities where coupling factors may have a vulnerability to a Comcast failure. And in this project, we applied a modified beta factor method that was designed specifically to allow for components to be members of multiple Comcast failure, Comcast component groups. Okay, so this slide just introduced what is the modified beta factor method. This method, or this model, assumes that the total failure probability of a component is an assumption of independent failures and dependent failures. Independent failures were defined as individual failures in the previous slides, and the dependent failures can be considered as Comcast failures. So the total dependent filter or the total Comcast filter consists of the contribution of each Comcast filters, as shown in this equation, where each Comcast filter is assigned a group beta factor, for example, the beta W. So each group beta represents the contribution of a single Comcast filter to the total filter probability. So, and this equation shows the independent filter probability or Comcast filter probability in terms of each Comcast component group beta and total filter probability. The challenge of applying modified beta factor model or multi-factor method is how to estimate the beta factors given a limited data scenario, because in the past, the estimation of the beta depends on the testing or operational data from the nuclear power plants. So to deal with that challenge, in this project, we applied an additive scheme partial beta factor method to estimate the betas. This method was developed by Humphreys and other people in 1987. So in partial beta factor method, a collection attributes called subfactors were selected, which are known to contribute to the provision of Comcast filters. So in a word, the beta factor can be considered as a sum of summation of these subfactors and then divided by 50,000. So this equation can be is applied in this work to estimate the beta factors. Okay, I will move fast because the time is almost there. Okay, this slide shows IRADIC CCF modeling process, a formalized process that relies on the modified beta factor method, and partial beta factor method is shown here. So this approach relies, the first step of this approach is to identify the Comcast filter groups, assign the Comcast component groups, and then define the beta factors by using the partial beta method, and then determine whether it's a single Comcast filter group or it's a multiple Comcast filter group, and then determine the probability of these Comcast filters, and then use them for the estimation of the filter probability of the DI&C systems. Okay, so that's for the reliability analysis, and the third part is a consequence analysis. So in this work, we just compares the changes of core damage frequency, but after adding the integrated fault trees of digital RTS, reactor trip system, and the SPOFs, engineered safety feature actuation system, to a generic PWR event tree model, which is shown here. This event tree is a generic PWR transient event tree, which also includes the ADWAS and anticipated transient without scram and the loss of seal cooling, yeah, and also the small break loca and medium break loca. So the reactor trip system filter is treated as an initiating event, and the filter of SPOF system is treated as an important basic event included in different top events, the fault trees of the top events. Okay, so yeah, so this slide just compares the original and new fault trees for the reactor trip system. The filter probability of the original fault tree is 4.3 E-6, and the filter probability of the new fault tree is about 1.3 E-6. So the original RTS is just a two-train analog for reactor trip system, but the new reactor trip system is a 4-division digital reactor trip system. So we can see that by introducing a digital system for the safety-related DI&C, its failure probability is reduced a lot. And this slide just compares the original and the new foot trees for the SPOFs. It's very similar to the comparison of reactor trip system. The probability, the failure probability of the SPOFs is reduced, and accordingly, some top events with this SPOFs failure inside has also, I mean, their probabilities are also reduced a lot. For example, for the low pressure injection, its failure probability is reduced from 8.4 E-4 to 2.4 E-4. Okay, so this slide just compares the core damage frequency with different RTS and SPOFs foot trees. So by adding the integrated foot trees of the 4-division digital RTS and SPOFs into the PWR model, the safety margin increased by the digitalization are quantitatively estimated. So results show that the core damage frequencies have been greatly reduced, especially for the transient scenario. The core damage frequency is almost halfly reduced. So the conclusion here is using the IRADIC technology shows deploying advanced digital RTS and SPOFs provides great benefits to the plant safety through an increased safety margin to the accident management. Okay, so next, just achievements of this project in the past 3 years, including the methodology development and some case studies applied based on the APR 1400 designs for the reactor trip system and engineered safety features actuation system. In this project, we are collaborating with universities, for example, the University of Pittsburgh, to develop new CCF modeling methods to estimate the software CCF probabilities. And we also have collaborations with North Carolina State Universities to develop risk assessment framework for AI-guided control system designs. We are also building up capabilities to address cyber vulnerabilities in digital and-C systems and networks. So far, we have 3 journal articles, 3 milestone reports, and some consequence papers published. Okay, this slide shows some other ongoing work of IRADIC in fiscal year 21 and this fiscal year. An integrated risk assessment of digital human system interface is being conducted for different digital feeder modes, considering software, common cause feeders, cyber attacks, and human factors. And this work is still based on the APR 1400 NC system design. The red figure is a flow tree we have built up for the digital human system interface. Okay, IRADIC development timeline and the status. This slide shows the work or the main achievements we have been made in the past 3 years. And for fiscal year 22, the tasks include the methodology development of the software CCF modeling, methodology improvement and the UQ, and further demonstration of occurs on human system interface, and also the uncertainty and safety sensitivity analysis, on a generic PWR model for different accident scenarios. And for fiscal year 23, the plan is to further develop and test the IRADIC software with a user-friendly interface, because after all, we expect this IRADIC technology can be applied by the industry to optimize their designs in early stage. So that's why we plan to formalize IRADIC as a software with a user-friendly interface. Another plan in fiscal year 23 is to develop is to deploy IRADIC for the design optimization and display application of some advanced digital and systems. So now we are seeking for the collaborations with the industries, including PWR honor groups and some startup companies, and see whether there are some common points we can collaborate. Okay, so there are some conclusions, but I will not spend too much time on this slide because time is very close to the end. Some publications, and that's all. Thank you.
Okay, thanks a lot for the presentation. Maybe we can allow 1 or 2 quick questions from the audience. Yeah, please let me know if there's any questions. Okay, maybe I can ask one. So it seems like you are doing a lot of risk assessments and also control system development for the PWR. So did you have any experience and had any ideas like, so now we have a lot of heat pipe microreactor design. So is it possible like we get rid of operators like early use the control system, or you early use based on machine learning or AI to control the future microreactor?
Thank you for the question, Jing. So first of all, I don't have much experience in the digital and designs. So the work in this project is to provide the risk assessment and also provide some suggestions for the designers to reduce their costs and the risks. So I personally do not have much experience in the designs. But for a question, of course, the design can be improved and optimized based on the risk information, the cost information, and that can be provided by this technology, especially for the safety-related designs, safety-related digital and designs, especially even for the macro reactor or for some advanced reactors or for some concepts like fission batteries. The safety is always a very important feature for them, especially when especially for the smaller designs, when the operator is far away and controlling and operating that system remotely. So that's why we said we can provide different information to optimize their diversity and redundancy designs and help them to reduce the risk and cost. I'm sorry, I'm not sure whether I answered your question, but that's just from my perspective to see what we can do for the designs and optimization for these macro reactors or small modular reactors. Yeah.
Yeah. Okay. Okay. Great. Do you have other questions from the audience? Okay. If not, let's thank our speaker, Dr. Bao, again, and hope everyone have a great day.
Okay. Thank you. Bye-bye.
Thank you. Bye.